Okay, we're going to do 3 derivative problems. In the first problem, we want the derivative of x cubed times the natural log of x. This is a product, so we will need the product rule. The derivative of the quantity u times v is u prime times v plus u times v prime. In this problem, u is the function x cubed and v is the natural logarithm of x. Following the product rule format, our derivative is u prime, which is 3x squared, times v, which is natural log of x, plus u, which is x cubed, times v prime, which is 1 over x. And then x cubed over x is x squared. We should simplify that fraction, and then we could factor out an x squared. And we're left with 3 times the natural log of x plus 1. We could write the 1 first. In the second problem, we also have a product, u times v. So we will again follow the product rule. The point is to show the derivative of the inverse tangent. So let's see. U prime is 1 times v, which is the inverse tangent. And then plus u, which is x, times the derivative of the inverse tangent, which is 1 over 1 plus x squared. And now we can combine this second term into a single fraction. So the answer is inverse tangent of x plus x over 1 plus x squared. The third problem, we have a composition. We have f of g of x. We have one function inside of another. So we have an inner function and an outer function. And the chain rule says the derivative of a composition is the derivative of the outside, leaving the inside in, times the derivative of the inside. Now our outer function is the logarithm, and we know the derivative of the natural log of x is 1 over x. When we do the derivative of our log in the chain rule, we want to leave the cosecant of x inside. So instead of writing 1 over x, we're going to replace that x with cosecant of x. Let me use the f of x notation. If f of x is natural log of x, then f prime of x is 1 over x. And we want f prime of g of x. So f prime of g of x, that means replace x with g of x. So it's 1 over g of x. All right, let's apply this in our problem. The derivative of the logarithm evaluated at cosecant x is 1 over cosecant x. So that's the derivative of the outside, leaving the inside in. So we don't write the x on the bottom, we write the inside function on the bottom, where the x goes. And then times the derivative of the cosecant, which is negative cosecant of x times cotangent of x. And then the cosecants cancel. Cosecant divided by cosecant is 1, and we're left with a final answer of negative cotangent of x. I would like to look at this problem another way. Let's let y equal the function that we're interested in here, the natural log of the cosecant of x. Then we are looking for dy dx. And the chain rule in the Leibniz notation says that dy dx is equal to dy du times du dx. Now what is this u variable? We're going to let u be the inside function, the cosecant of x. That means then that y is the natural log of u. And now dy du is 1 over u, and du dx is negative cosecant of x times cotangent of x. And then back substituting for u was cosecant x, we get our answer, 1 over cosecant x times negative cosecant x times cotangent of x. And again, the cosecant cancels, and we're left with negative cotangent of x, which agrees with what we did the first time. So there's a couple of ways to approach the chain rule. One is with the f prime notation. The derivative of f of g of x is f prime of g of x times g prime of x. And the other is to unravel the function using an intermediary variable and saying that y is equal to the natural log of u, where u is the cosecant of x. And then the chain rule in the Leibniz format, dy dx equals dy du times du dx. dy du comes from the derivative of this equation, and du dx comes from the derivative of that equation. So you just multiply those together, and you get almost an answer. The problem with this expression is that it has this variable u in it, which we just created out of thin air. So we just replace the u in the next step with the cosecant of x, and then simplify our answer, and there it is.